welcome back to the podcast. Decouple, of course, and we are back with Nick Touran for a triumphant second visit, I think in under a month. Nick, I realized how much I missed you after our sort of 2-year hiatus. Yeah, really enjoy having you on, man. The nuclear historian hat is one that I like seeing here on Decouple. So thanks for making the time
Yeah,
again.
no, thanks. Absolutely. Always a great pleasure. Happy to be here.
Okay, so we've been chatting a little bit. I had Noah Retberg on recently. We were talking about process heat, and it led to a discussion that was pretty heavy on gas cooled reactors. I have been wanting to tug on the thread of breeders. I have a friend, Nate Hagens, who's a bit of a nuclear skeptic, and he asks all kinds of wacky questions, like, what if there was like a electromagnetic frequency pulse and every reactor on Earth was, all their safety systems were scrambled? He asked these kind of questions that I'm not used to really dealing with, because in my advocacy, we've even moved past a lot of the radiation fear mongering. We're solidly into questions of economics and speed of deployment, which I think the antis, that's a fair ground for us to be responding on. But what one issue that comes up, and I know you've dealt with it on your blog, is how much if we did go as nuclear as some of the nuclear advocates want us to. Again, whether that's achievable in terms of constructability and everything, we'll leave that aside. Would there be enough uranium? And of course, that leads into this breeder question. And I guess historically, that's why we even talk about or started talking about this miracle of a machine that can produce more fuel than it consumes. So I've been curious about that. I've been guilty of not tugging on these threads. So I wanted to have you on for an episode on breeders. Yeah, I know that's something that I think you're pretty passionate about. And again, as the nuclear historian, what's new is old, it seems, in nuclear, particularly kind of in the so-called advanced side. I'm curious about the whole topic. So I don't know where you want to jump in. If we want to go back in history, you take it away.
Yeah, well, I guess we better just start at the beginning, which we talked about a little bit before, but it's worth going over again, I think. And at the very beginning in the Manhattan Project, after Hanford B came online, the team who had designed and built Hanford B started thinking about the future. What are we going to do with this amazing power source going forward? How to do civilian power? And at the time, they really were under the basically false impression that there was just a few thousand tons of uranium ore on the planet. And they really thought it was a very limited resource. And so they thought, well, the only possible way to make any meaningful amount of civilian power from this technology is to use a breeder technology, which they had realized was possible back in 1942 before CP1 turned on. But so a lot of the early concepts and the early thinking were really about breeder reactors. How do we get breeders? And that was targeting civilian power because of this perception that uranium was very rare. And that's why, one of the first reactor that ever made a certain amount of electricity, EBR-1, lit up those 4 light bulbs. That was a breeder reactor because they were trying to develop it again for civilian power. Now, as it turned out, just fast forwarding, in the mid and late 50s, we discovered vast quantities of uranium ore all around the world, in the American West, for instance, and many other places. And so pressure on uranium ore really reduced, and it was okay to be much less efficient than you can be with breeders and make a significant amount of civilian power. And so turned out breeders they're a bit challenging to build and operate. They have complications. And so it was okay and appropriate to just build a fleet of non-breeder reactors, which is what we have done today. And that's been okay. We haven't really run low on uranium yet, but we only make 4% of the world's primary energy right now. And so it's still a concern. So when you start saying like, okay, well, let's make 50% of the world's primary energy. Now you can start saying, okay, at some point, uranium ores will become a little bit depleted, and we're going to have to deal with increasing uranium prices. And at that point, breeder reactors all of a sudden become interesting again. And so looking at a large-scale expansion of nuclear really makes breeder reactors a necessary and important topic to develop and talk about. That's kind of the initial cut.
Yeah, no, that's a great sort of backgrounder. One of the selling points of nuclear is, that there's this high capital cost, but the fuel costs are so low. Were prices for uranium, very high early on, and how inefficient are our light water technologies, and I guess our heavy water technologies as well, when it comes to actual fuel utilization compared to what's possible in a breeder.
So yeah, fuel cost was significant in the beginning. I mean, it was all owned, and in the early days, it was all owned by. You couldn't even own nuclear fuel; you only could lease it from the U.S. government. That's in the U.S. at least, and similar in other places. It was extremely expensive, and it was a major impact on economics. That's kind of changed. I mean, since we found more uranium now. Large fleets. I mean, we heard at one point the French fleet was saying uranium price is like 5% of their total cost. It was like basically not trivial, but and it's higher than that in some places. And then I mean, and it's been increasing more recently. So it's but anyway, it's certainly not the majority of the cost, like for a fossil type plant, which is all fuel cost. In general, we get about 1% of the total energy out of the mined resource. So if you look at the whole fuel cycle, you dig up a bunch of uranium, you then enrich it, and you get all these tails, and then you take that enriched part and you burn maybe 5% of the enriched part. But if you include the tails, you've only really gotten about 1% of the total energy out of the stuff that you pulled out of the dirt. Whereas if you do go ahead and recycle and use breeder reactors, you can take all that uranium 238 or thorium 232 if you're using thorium, which no one's doing. But anyway, and you can get like 90% of the total energy out. You'll never get 100% because there are process losses. When you do recycle, you're going to have some streams where you didn't get every single actinide back into the reactor. So 90% is kind of a reasonable goal that's definitely achievable with recycling. But yeah, we get about 1%, maybe a little bit less in the current fleet. And that's similar for LWRs as well as Candus.
So, another rationale you hear for breeders is that it can minimize nuclear waste, I guess, from its own power production, but also potentially by consuming the waste of other reactors. You mentioned those tailings, and that seems like some low hanging fruit of U-238 to turn into U-239. Talk us through a little bit about that, because that's certainly the waste side. It
Yeah.
seems to be a big part of the rationale.
Yeah, this is a major sort of interesting thing that you can do with especially fast neutron reactors. So there's kind of two waste streams. There's the tailings from the enrichment plant, which are just uranium 238. It's not high level nuclear waste. It's a low level industrial waste. It certainly is, problematic. It's chemically toxic for one thing, and being
It's
able
like
to
lead,
take
right?
that stuff and
In
yeah,
terms
it's
of the
like lead.
chemotoxicity. Okay.
Yeah, and I don't think it's quite as neurotoxic as lead, but I'm not 100% sure on that. But yeah, I mean, think of it like lead because of the radiation. It's mildly radioactive. It has a 4 billion year half life, so it decays very slowly, meaning it's not shooting out energy very fast. But anyway, so that's one way stream, and yes, through breeding, by taking that and loading it into a breeder reactor, converting that into plutonium 239, and then fissioning the plutonium 239, you can turn that sort of industrial waste resource into a vast amount of energy, which is exciting and interesting. But it's not nearly as interesting as the other part of it, which is to take spent nuclear fuel, highly radioactive, high level waste out of a light water reactor, for instance, and then recycle that back into a fast neutron reactor. Now something really interesting happens. Not only can you get more energy out, you got 5% first go around, and you can get more and more, but a lot of the really long lived parts of nuclear waste, plutonium, americium, neptunium, curium. Those are heavy nuclides. The uranium didn't split. Sometimes a neutron goes into a uranium atom and it becomes the next thing up. And it just kind of goes to these very large actinides. We call them transuranics or minor actinides. And those are the dominant heat source in the long-term nuclear waste repository design. Those are the 100,000 year, the 10,000 year nuclides. And in a fast neutron, if it comes along and hits those, it can directly fission them. And so you can actually fission those minor actinides, transuranics, to get more energy out of those. And when you do that, you change them into fission products, which only have, up to a 500-year half-life. And so the repository, the demands on the repository become much more practical. Like you don't have to design a repository that's going to last for 10,000 or 100,000 or a million years. You only need one that's going to last 500 or 1,000 because your nuclides are decaying much faster. And so this is this sort of partitioning transmutation concept where you can really reduce the overall radiotoxicity versus time of nuclear waste itself by directly splitting it. that's intriguing to people. It kind of sounds like we're just solving the nuclear waste problem, and so that's really inspired a lot of interest in fast reactors.
Not to go too off track, but I've seen some research. I think it's Canadian. Because we have these insane ore grades up in the Athabascan Basin. I think the world average is probably under 1% uranium in the ore, and we get up to 20%, and there's even pockets within those areas which are like 60-70% pure uranium in the Athabascan region. So there's some analysis of looking at putting spent fuel back underground and at what point it reaches a similar level of radioactivity, because it's, I think, after 600 years it's mostly driven by transuranics, decay very slowly and are basically just giving off alphas. And that's an interesting way to think about sort of this circular economy, if you will, or circular waste stream of kind of returning it to the land. But I don't want to jump off too much on that trend. You describe sort of two potential, enormous sources of fuel, the tailings versus the spent waste, which is highly radioactive. One of those sounds a lot easier to handle. Do you feel like the discourse, because waste has been made into such a bogeyman, the focus has been maybe too much on, well, let's reprocess, spent fuel from our light water fleets, and not enough on the on the tailings. I know Edward Teller would walk around these areas where there was tons of U-238 tailings, and from the enrichment process, and say, hey man, we've got gazillions of years of nuclear fuel here.
Yeah, I mean, it's kind of hard to do. It's hard to get the energy out of the tailings, of the U-238 tailings, without doing the high radiation recycling. There's some ways you can talk about doing it with like deep burn ones through cycles, but those are in development, require very fancy materials. The traditional idea is you load it up in the fast reactor, you build up some plutonium, and then you move it into the chemical plant that does hot chemistry on it. It melts it down, separates it into its constituents, and then refabricates new fuel, very radioactive. So this whole process is under extreme high level waste radiation constraints, and so you really can't access the energy without doing the recycling that you would do with the light water reactor spent fuel anyway. So they aren't super decoupled. I mean, you really need to have a recycling plant like that up and running in order to fully utilize the tailings. So I don't think you could just say like, oh, let's just grab the tailings and breed off of that without being able to do the light water recycling as well. Again, except in the exception of the deep burn once through cycle.
I was just looking into this, prepping for this interview, looking at the Phoenix and Superphénix program in France, and interesting how it sounds like the original rationale for breeders was that perceived shortage in the 50s. But I think the OPEC crisis trauma was so deep in France, and maybe they were thinking about being cut off from their African colonies in terms of that source of uranium, that was a renewed interest in breeders at that time. And I may have misread this, but they were, I was reading some documents which were saying that, if they just had 20 breeder reactors, they could make enough fuel for their light water fleet. So are breeders not just about running a reactor kind of forever because it makes more than it produces, but also providing fuel potentially for their traditional light water fleets, so they have that synergistic possibility?
Yes, that's what I would kind of call the traditional fuel cycle view with breeder reactors, and many countries have considered exactly that. It's sort of been acknowledged that, okay, the fast breeder reactors with somewhat exotic coolant and an extra loop are complicated. They're generally considered more expensive to build and operate than like a light water reactor, which it's with its nice simple water coolant. And so what people imagine is exactly what you described: a fleet of light water reactors, and then a smaller number of fast reactors providing fuel cycle services, as they call it. And that would be, yeah, you take the waste out of the light water reactors, you refabricate it, put it into the fast reactors, you do that transmutation to make the waste last longer, and you also do breeding. You breed additional fissile material, and then you pass that back into the recycling plant, and then that plant can be fabricating fuel for the light water reactor fleet and for the breeder reactors. And so you get this situation where those fast reactors are really extending the uranium resources dramatically, a lot more than they can do without breeder reactors. I mean, you go from that 1% to the 90%, and you still operate a bunch of light water reactors because they're relatively reliable and easy to operate, but you just fuel them with this bred fuel amplified by a smaller fleet of breeder reactors. And yeah, the number it depends, what type of breeder you have. Well, there's different conversion or breeding ratios that say how much plutonium you get versus how much you put in. And so you can have like a ISO breeder, which just makes the same amount. It just, you put in one plutonium and you get one out. Or you can have like big breeders with big breeding ratios where you get 20% or 30% more fuel out every time you do it. And depending on which one of those you do, that'll determine how many breeder reactors you need to have to service a whole fleet. And yeah, that's been the plan. I mean, France had that plan. The United States had that plan with our Clinch River program, which was a massive program. And pretty much the Russians have a similar plan with their VVERs. They want to do a fleet of VVERs with a few BN fast reactors providing fuel cycle services. So yeah, that's the plan.
Okay, so you said it's the plan, and listen, this virtuous cycle sounds pretty amazing. It also sounds incredibly complex in terms of what I'm guessing are like kind of the hot cells to do this work, the chemistry, and I guess some of the concerns around proliferation actually led to this being squished a bit by Jimmy Carter in terms of I believe the 1, 2, 3 agreements. Could you go a little bit into that, and then I think we'll talk about why, if the dream is so amazing, it hasn't really materialized. Or I'd just like to know how far it has gone in certain countries. And it seems like Russia is the most advanced, with really the only commercially operating fast reactors in the form of again, that BN series of sodium fast reactors.
Yeah. So yeah, I mean, you're absolutely right. There are concerns and issues, and when we in the United States, when we decided, okay, we're going to dedicate our full industrial resources to the development of the breeder reactor in 1968 or so, and the entire Atomic Energy Commission shifted all of its resources to develop this Clinch River breeder to make this kind of thing happen. Well, yeah, the biggest concern they came up was the one you mentioned, which is a proliferation concern, where if you do have a facility that can take nuclear fuel and melt it down and separate it into its different elements, and then you'll have one batch of that, which is plutonium, separated plutonium. And if somebody comes in there and grabs that, that's weapons usable plutonium, even if it's slightly, if there's the isotopics don't have to be perfect for plutonium to be weapons usable. And so there's this huge concern that, well, I mean, obviously the United States already has weapons, so who cares? But if we go and do this and say this is our energy future, then that's going to inspire other countries who are going to want to go recycle. And so let's just not do it at all as an example. And then we'll be able to say, oh, no, you don't need reprocessing to have an energy future. And so that really became the major political opposition to the concept of breeding. People called it the plutonium economy. And that really, I mean, that took a lot of the wind out of that particular program in the United States. And similar things happened elsewhere. I mean, in France, Phoenix was built and operated well. At Superphénix, which is 4 times bigger, a gigawatt scale sodium cooled reactor, met unbelievable opposition. 60,000 people protesting in the street. I mean, it was the heyday of anti-nuclearism at that point. It was extremely unpopular, and there were technical challenges as well. And those things came together and basically shut down fast reactor programs basically around the world. Russia is the exception. I mean, they have maintained their operation of sodium cooled fast reactors throughout. I mean, since the beginning. I think their first one was in the mid 50s, and they've maintained operating fast reactors ever since. And they now have the only commercial operating sodium cooled fast reactors. But again, their plan is still, they don't necessarily plan on just doing all breeder reactors. They plan on using a few of those to provide fuel cycle services for the VVER LWR fleet.
So they plan on it. I mean, have they done it yet? Has this dream, this virtuous cycle materialized yet in any way, shape, or form? Has been demonstrated, or it's still theoretical?
I think they just recently loaded up recycled MOX fuel into the BNs that came from a VVER. So it's been like token demonstrated. Like, it's not really up and running in full swing, certainly. They don't have enough fast reactors to do it in full swing anyway. But so yeah, it's certainly conceptually proven. It's like clear that it's possible. There's no major technical thing in the way that needs to be demonstrated. It's just, I mean, another thing that should be said is, like, it's expensive. If you are taking highly radioactive material and melting it down and separating it into its constituents, it's not just a hot cell. It's like a hot cell factory, like a huge hot cell. There's a small example in Idaho that you can take a tour of. very expensive, complex remote machinery doing complex chemistry and fabrication. And so the cost of that has just been very high. It's much, much cheaper to just go mine cheap uranium, enrich it, fabricate it, no radiation, and then run it in the reactor and then put it in the dry cask. Like that's cheap, relatively cheap. If you put in this other, the recycling, refabrication step more than doubles the total cost of fuel. And so as long as uranium is plentiful and cheap, there's really no economic reason to do the recycling. The waste thing is cool, but it's like not essential. I mean, the waste repositories that people are designing are perfectly capable of handling non-transmuted, longer lived waste. And so that's an okay option. And until uranium becomes very expensive because it gets rare or whatever, the economics of recycling just don't really work out. So those are the two major kind of concerns. That's why we aren't seeing it a lot. People say, oh, we should be recycling all the time because it's more efficient. It's like, well, do we need to double the cost of nuclear fuel right now? Is that what the nuclear industry needs? Like, probably not. Like, we might want to ramp up demand first.
And it's interesting, like just when we talk about economic cost, and it's all abstracted into, monetary instruments and imaginary tokens of value like dollars and euros. But like what I see pragmatically in the trenches, advocating for nuclear, working with labor, working, consulting with government, et cetera, is, monetary resources is not the only thing. Human resources are a major, major constraint. Like here in Ontario, we're talking about running 4 or 5 refurbishment processes simultaneously, like nationally and internationally, building a bunch of SMRs, potentially building a bunch of new large reactors. And we've got a pretty hot supply chain and a decent number of nuclear professionals. But imagining, just the human resources, that ultimate currency, I think that makes the whole thing work until our AI, driven robots can sort of do all the work for us. That's a big constraint. So we've talked a bit about the political barriers, the proliferation barriers, some of the economic barriers. What about the technical barriers? Like, what's been the performance? And I guess we're talking basically exclusively about sodium. Although I guess there's a bit of lead, but to not complicate it, let's focus on the operational experience of sodium fast reactor.
Okay, yeah, and yeah, there's kind of two. There's the reactor performance, and then there's the recycling refabrication performance. So let's focus on reactor performance. It's been mixed. I mean, if there's about 500 reactor years of experience with sodium cooled reactors. The vast majority of them have been fast neutron reactors with no moderator. There have been four sodium cooled reactors that had a moderator. 2 for submarines, 2 for power, but those are kind of niche. Those are those sodium graphite reactors. But yeah, overall, many countries, US, Russia, France, UK, Germany, Japan, Italy, India, China, have all built and operated sodium cooled fast reactors. The first one, well, it wasn't sodium. The first liquid metal cooled reactor was the Clementine in the United States, which was started up in like 1946. That formed the basis of liquid metal cooling. EBR1 in the early 50s was cooled with NaC, sodium potassium eutectic. So you just mix the two metals and it ends up melting at a much lower temperature, so you don't have to keep it as hot. Fermi 1, I mean, there's a bunch of reactors. Let's start with some bad experiences. I mean, EBR1 did demonstrate breeding as a concept, so we knew that we could actually breed, which is great.
This was the 4 light bulb reactor, yeah?
Yeah, the 4 light bulb reactor in Idaho. Great museum in Idaho. Definitely recommend going. It's only open in the summer, I think. But anyway, that reactor operated okay. It did have a core melt. It melted its whole core melted. It was small. It's like a basketball-sized core. They suffered a core melt for various reasons. They recovered it. They pulled it out and put a new core in. Fermi 1 was a big effort by 23 utilities, as I was saying last time, to build a commercial reactor in Detroit. And this is we almost lost Detroit reactor. They also suffered, they had very poor operational experience, lots of problems, lots of leaks, lots of issues, just dealing with, I mean, sodium is not a coolant that people have dealt with nearly as much, especially back then. And so just figuring out how to keep everything sealed and keep air out and have leak detection. And if you have a sodium water steam generator heat exchanger and there's a leak, you have to be able to detect that leak quickly and put that tube out of commission. And so there's all sorts of challenges, just plumbing and exchanging heat with this kind of a coolant. And so that had a bad experience. There have been good experiences too. I mean, EVR2, which was also a relatively small experimental reactor, operated great. It was a beautiful reactor. It was the first one to demonstrate passive safety, which we all sort of know and love as the foundation of Gen 4 type safety systems, where they did this amazing test in 1986 where they invited a bunch of people out and they did a test where they just turned off the primary pump and did not insert any control rods, and the reactor with its passive safety went down to really low power and cooled itself.
Was
to
this
natural
before or after
circulation. And
Chernobyl? Because you hear about like the sort of cowboyism of the Chernobyl accident, and you're like, man, it seems like a lot of people were doing this from time to time.
it was literally 2 weeks before Chernobyl.
Wow.
So I mean, it was this great success, and everybody was. It was much more carefully done. I mean, it was very well analyzed, and they had their predictions, and anyway. And they did another test where they shut down the heat removal system as well, and it did the same thing. But it was basically a revolutionary safety performance, but no one ever heard of it because Chernobyl happened 2 weeks later, and so the news of this great safety of a nuclear reactor got basically washed out. But yeah, that one didn't do
So
well.
we hear about that passive safety, but it sounds like there's the problem with sodium fires. You're I think often separated by a couple loops, but you end up having a water interface at some point where there's the potential for some, I guess, mechanical breakage, and sodium and
Yeah.
water are exciting. I remember that from chemistry class.
Yeah, it's less exciting if there's no air, but yeah, I mean, air, like, it's certainly an exothermic reaction. It's basically considered an operational experience these days. Like, we have dealt with sodium fires for many years. Most of these reactors have had dozens of small sodium leaks, and there's inerted cells. I mean, the concrete, there's a sodium concrete reaction as well. So like the concrete is lined with liners that prevent that. There's inert double walled pipes. There's leak detection, acoustic leak detection, different ways to isolate it. There's sodium fire protection systems. So it's kind of like a thing. Like, you can deal with sodium fires to a degree. Whether or not it's going to be reliable in fleet mode is to be determined. We just haven't built enough of them in fleet mode to say that, like, even though that there can be a sodium fire, we think we can handle it at a rate that's sufficient to get a high capacity factor. That's kind of like up for debate. There certainly are examples where a small sodium leak led to major outages, like at Manju in Japan. There was a little thermocouple sticking in a pipe, and it was vibrating in the flow and eventually sprung a leak. And they had a 10-year outage just to deal with that sort of small thing off in a secondary loop. And so those kind of challenges. And Rickover has a bunch of kind of classic quotes about using sodium in a submarine. Always fun to go read those, because they did the Seawolf was this sodium cooled moderated reactor where it was beryllium moderated, where they were attempting to get high thermal efficiency and be able to run without mechanical pumps, because you can pump liquid metal with like magnets instead of pumps, which is cool. But boy, was it hard. I mean, in the confined space of a submarine, it just is not practical. And he kind of ripped into it as they dealt with various maintenance issues. It was just so much easier to send people in to go in and fix little issues that happened with water coolant than with the sodium system. So it's pretty clearly not good for a manned tiny compartment deep underwater. But that doesn't necessarily mean it's not good for a terrestrial plant. So anyway, I would say sodium fires are a concern, but they aren't a showstopper. Like, we consider them a thing that we expect and plan for and design for.
And you mentioned trickier. I think we talked about this in a previous episode, but a little trickier to maintain than water, because water is such a amazing shield in terms of refueling and other issues. Um, what I saw, like looking at, I think it was the Superphénix. I mean, they had miserable capacity factors. A lot of that was administrative and protest related, and I think in their final years they got up to sort of 90% capacity factors. The BN fleet, I think, it's certainly not as economic as the VVER fleet, and I think cap factors are kind of 80s. What explains that? Because I think there is online refueling with a lot of these reactors, so they hypothetically should
No,
do better.
no, I mean, the refueling is actually more complicated because of what you said. Like, with water, you can just open up the vessel head and go down in there, and you can see all the fuel, and you can go down with cranes and pick it up and move it around. But with sodium, you have a sealed system. It has to stay sealed at all times. So when you're moving fuel around, and they don't have online refueling. They all,
Okay.
as far as I know, they've all had manual fuel management roughly on. I mean, Phoenix had to refuel every 2 months, but it was a small sort of research reactor. But yeah, you can expect refueling outages every 18 months or so in a typical SFR. And they basically have like a really big, complicated sealed head that rotates. And within, there's this big rotating wheel. And then within that wheel, there's like other wheels that rotate inside of it. And there's these machines dangling off of them that can kind of like traverse the whole core underneath. And you can kind of go down there with computerized. It's opaque, so you can't actually see through sodium like you can with water. And so you're going down sort of with computers and sensors to try to figure out like which assembly you're going to pick up. And then you pick it up and you have to transfer it through this. You bolt a thing onto the top of the head and you pull that assembly up into this cask. And then you can kind of pop that off and move it to some other place. So, I mean, the fuel management, fuel transfer stuff is all way more complicated with sodium than it is with water, which you can just, again, open up, have direct access to and see. And so that's one major, I mean, if you're doing a lot of fuel management, it can take a really long time. So that's one thing that could explain, longer outages. But also there's just more equipment. I mean, if you have, as you said, there's more loops. You have like a primary sodium loop. That primary sodium becomes extremely radioactive. Neutrons get absorbed by sodium and become activated. And then if you're going to a water heat exchanger, you can handle the chemistry between sodium and water, but it's too much to handle chemistry plus radiation. So if you have a sodium leak and it starts a fire in a steam generator, you don't want that to also be a radioactive sodium fire. And so they always do an intermediate loop where you transfer primary radioactive sodium to secondary non-radioactive sodium, and then that secondary non-radioactive sodium goes to the steam generator. And so what you have is, VWR just goes water to turbine. PWR goes water, water, turbine. This goes sodium, sodium, water, turbine. So there's a third loop, and that has more instruments. It has more valves, pumps, things that can go wrong, things that need maintenance. It's just more equipment. So it's additional capital costs. It's additional operations and maintenance. And so that additional loop has been in the literature blamed for like a roughly 20% overall increase in total cost. Those are the main explanations.
And I've heard that there's hope with the again, economies of scale, moving to the BN 1200. I guess it's gone like 365 to 6 to 800 to 1200, that you might start to achieve some economics that are kind of on par with a light water reactor. Are those rumors you've heard as well?
Yeah, I've heard the same thing. And yeah, I mean, you'll never find a reactor team that says a reactor just is never going to be economical. They always say, well, if we just do this one thing, it'll then become economical. And so yeah, right now the Russians are basically saying like, yeah, our current BN reactors are not going to compete with the VVERs on economics. But yeah, maybe if we go to 1200, that's when we think break even might actually happen. And then they're also saying, well, maybe lead will be better. And so they're building a lead cooled reactor as well. And so those are kind of their like fork in the road in terms of, seeing what they can do in terms of improving overall economic performance. So we'll see. I mean, you can never, it's feasible. It may make sense, but you cannot know those kind of things without building it and operating it basically in fleet mode for a couple decades. So it's a hard thing to verify.
So I have this thesis, and again, I'm a non-expert, and often I'm pretty insecure in my opinions, although I guess I have strong opinions, loosely held, hopefully. But, in terms of just like, what I'm most familiar with looking at Candu development, starting with this kind of Manhattan North, not as big of an investment for Canada and the European partners as the US made with the Manhattan Project, but a huge mobilization of financial resources, which in turn, also human resources and the development of those human resources, iteratively led to, a series of reactors that proved the concept of, heavy water, moderation, moving from a national power demonstration of 20 megawatts up to a commercial plant that wasn't all that economical at 200 megawatts to 500 and onwards. But a process of like 50, 60, 70 years. I see. I had this tweet about reactors that have advanced versus should probably be what we call advanced reactors. But I see other chemistries and approaches, and I just don't see that they're anywhere near being commercially viable. And thinking about molten salt reactors, for instance, where the entire sort of operational experience has been within national labs, where there's been a lot of troubleshooting, and like there should be a lot more troubleshooting, and hopefully we can figure it out eventually. But it seems to me naive to think that we can leap from a national lab to commercial operation, with a startup company driving that. And it seems like the sodium fast reactor experience is illustrative of that as well. I mean, the Russians have been at it since the 50s, and there may be, in the next 20, 30 years, might achieve economic parity with an LWR if they get the BN series up to, a really massive size. That may just happen. But to me, that just seems kind of illustrative of the march of technology development that's required, but it also poses major questions in terms of who pays for that cost. The initial addition, the initial sort of national lab work in Canada, obviously it wasn't commercial, the development of a national power demonstration reactor and even Douglas Point. And we're not exactly in a heyday of investment, particularly state, run investments in kind of blue sky R&D that doesn't demand a return on investment horizon. And so it just seems like it's a very hard moment for some of these other advanced technologies to come into being and to try and get to commercial deployment. This is a bit of a long commentary / question, but does that ring true to you in terms of what we're seeing here with the development of sodium fast reactors?
It's kind of complicated. Sort of. I would say, it takes time and money. Developing reactors to commercial viability takes time, smart people, and a lot of money. And where exactly that money comes from doesn't totally matter. If you have people who if you have private investors who are willing and interested in throwing in a lot of money to do development of reactors, then that can work just fine. It'll take a long time. They may not see a return ever, or it may take a very long time for a return, but they can understand that risk. But because maybe the upside is so great if it works out that they're really excited about it. It's a meaningful thing to do to try to, solve major world energy issues. And so, who's to say, private finance can do whatever they want. And if they want to throw money into advanced reactor development, that's awesome. And I will happily help out. On the other hand, where's the limit? It is very expensive and it takes a very long time. So how many people are going to be able to take this to fruition? You kind of start when you first get into nuclear, you think, wow, nuclear is so cool. The people who did it in the past didn't know what they were doing. They didn't think about economics very well. And so why don't we just do this one cool trick? The certain combination of fuel, moderator, coolant, whatever. And it's just it's going to be great. And so I think there is a risk that people think that it's going to be fun and easy to develop nuclear. But all the history shows that it's not. It's very hard. It doesn't get hard until you're up and running. Construction shouldn't be hard, but it is anyway. But even after construction, that's not even the hard part. The hard part is after you turn that thing on, achieving efficient, reliable, maintainable operation. That's the real challenge. And nobody's, all the startup folks aren't there yet. Everybody's sort of in the design, licensing, construction phase. So we haven't even gotten to the hard part. And the real question is, once you get into that, will you survive? Will the money keep flowing? Will people lose interest? There's all sorts of cases where a reactor started up and was just performing pitifully, against all expectations. People thought, whatever, we talked about them last time, the superheat reactor is going to solve all of our economic issues. Well, it didn't. It operated terribly. And then the people financing it shut down. So whether it's government or private finance doesn't really matter. It's just who's going to be able to keep interest long enough to get it over that hump. And then, you can ask well, we already got over that hump. And I know we talk about this all the time, Candus and LWRs are already over that hump. We know they can operate reliably. And so there's some reasonable statements to be made about if decarbonizing is a major emergency, let's just build a bunch of those to kind of get that taken care of. Well, in the meantime, working on the tech development and working on getting a couple of these prototypes up and running and vetted out and to see how well they can be maintained and operated. So, and if you're a taxpayer, that may be a more appropriate type of approach.
It's interesting. I love this. There's the challenges of construction. The real challenges begin with operation. But even an additional challenge is, can you squeeze more than 30, 40 years of life out of your reactor? And I think that's been not the only curse of the advanced gas reactor fleet in the UK. Not a fantastic operational record, but certainly I think if Candus couldn't be refurbished, that would be a reason to say, you know what, let's toss these in the can and we'll just go the LWR route. But because we have that opportunity for refurbishment, we can make these assets, much more economic because the upfront costs are huge in nuclear. Yeah, I mean, it is interesting. I think that the money coming in, and God bless it for coming in and doing this work, is coming in, perhaps making that category of the kind of development pace that's possible with things like consumer electronics or tech or software. And like, does it have to be so slow in nuclear? Is that just a reality in terms of the size of the asset, the complexity of the work that needs to be done, maybe the human resource bottleneck?
No, it definitely doesn't have to be. I mean,
Is
this
it
idea of the
regulation, over
national
regulation? Like what's
I don't think so. I mean, people want to build products. Like no one wants. It's not as exciting to say like, let's go build a little prototype reactor at the National Reactor Testing Station, which no longer exists. I mean, it's Idaho National Lab now, but like people want to like get right to it's like, if we don't decarbonize in 6 years, we're all screwed. And so we need to be pushing out commercial entities. And so there's a lot of focus on like, just get to commercial like right now. And there isn't really a venue at the moment where you can say like, let's build five 5 megawatt reactors of all the different advanced types in a place where the same team can kind of go and learn from each other and try them out and see how they operate and iterate on them quickly. That's just isn't a thing we're doing right now. We certainly could. There's nothing really holding us back on that. It's just not where the money is focused. Like the government grants that come through are like, I want something that's commercialized like right now. There isn't a lot of motivation to just go off and do like, let's do reactor playground. They aren't cheap. I mean, operating even small reactors will be expensive. And if they don't have a revenue stream, like, okay, they aren't going to pay for themselves. But that's how you could certainly get a lot more operational experience and pick and relearn, how to operate a bunch of different reactors quickly would be to build little small ones in sort of a remote area. And so just like finding where to fund that from is the big challenge. Nobody wants to fund that right now. But there's no like technical or regulatory reason why you couldn't do that. I think that'd be cool. But I mean, I'm a nuclear engineer, so of course I do.
So one of the things I hear a lot, and helpful to be a Canadian here and maybe have a perspective that's a little bit removed, but in terms of what comes out of the DOE, there's a bit of a concern. I mean, there's the strength of the American nuclear sector is the operations of the existing fleet, absolutely phenomenal, and I mean not unique in the world, but amazing. Definitely a weakness is construction. Another strength that's touted, and I think historically this is very true, is like, listen, we developed the basic reactor technology that now underpins everything but the Candu. Well, not everything, but you know what I mean, the LWR fleets, which have come to dominate in the world. And so I think there's a desire in that insecurity of like, yeah, but we're not actually constructing everything and we're actually facing major difficulties. There's a desire to sort of salvage that by saying, but yeah, but we're still, at the forefront of developing novel reactor technology. Do you feel that's true, or and the other part of the question, I guess, is this sort of the tacit knowledge of actually running a variety of these reactors, as the Russians are doing with the BN side, and then we're developing a lot of reactors here in the West, and maybe at the forefront of developing some of the Gen 4 concepts, but we're certainly not actually getting them constructed and built and accumulating that tacit knowledge, that operational knowledge, as say the Chinese are with their HTGR and molten salt reactors, and I think even they've got an operating sodium reactor. Like all the sodium reactors in the West, not a few of them were commercial, most of them were research, and they're gone from what I understand from my brief Wikipedia research.
Yep, that's true. That's accurate. Yeah, I mean, you cannot argue today that the U.S. is at the forefront of operating advanced reactors. Certainly, I mean, China built a thorium molten salt reactor that they're about to turn on. They've got the HTGR, as you mentioned, and they have CFR, and they're constructing two big 600 megawatt sodium cooled fast reactors well under construction. And Russia's operating sodium cooled reactors and so on. So, like, yeah, it's just obviously the case that they have more up-to-date operational and construction information about those types of advanced reactors outside of this country. We may have more people working on it, more startup companies, more papers, and so on. But in terms of actually building and operating, we're certainly behind.
Yeah, I mean, this raises kind of broader questions, and I think we discussed this a little bit previously in our innovation episode, but just about which sort of political systems are most conducive to innovation. And I guess, I think you could probably make a solid argument that, liberal democracy, free market systems excel. But perhaps not if you don't actually have some blue sky state funded research, or there's just not the dollars to do it. Ultimately, if there's some money to make it happen, that probably would be one of the key variables to actually achieving the liftoff. As liftoff is such a buzzword these days.
Yeah, but I mean, the innovation that we did in the United States in a liberal democracy in the olden days is just astounding, as we talked about. I mean, there's just dozens and dozens. We built all sorts of crazy reactors and operated them and got all sorts of experience and repaired them, and it was just fantastic. The innovation and development that we pulled off was truly astounding. And yeah, it's the funding source. Like the Atomic Energy Commission was highly funded and was tasked with developing commercial nuclear power for the good of the nation, and that was a big amount of money. And a lot of work was done because of that. And a bunch of super smart people and lots of other great resources were thrown at that problem. And so it just comes down to like, what are you going to fund?
And that seemed like it was still capitalism back then. But nowadays, like if you were to have that kind of level of public investment, and you'd have screams of and accusations of not just kind of Bernie Sanders socialism, but probably communism for.
I mean, yeah, nuclear became very unpopular. Like, it's hard to do publicly funded or publicly funded R&D on a technology that is deeply unpopular. And so it really has to do with just like how people feel about it. And so, maybe not right now, nuclear is becoming much more popular, driven largely, I think, by concerns about climate and energy scarcity. So, we could get back into that, but it really is coupled to like public perception. Like, no taxpayers are paying a lot of money for something that they think is horrible or bad for the environment.
So I mean, I really do want to drill down again a little bit on sort of the operational experience and your sort of level of optimism or pessimism, because it does seem like, and I'm very curious about this, that the Superphénix did get up to a pretty decent capacity factor, at least for the final year of operation. It is possible to run a sodium fast reactor well, although I guess still not kind of hitting economic parity with PWRs. But is it trickier to get there, again, just in terms of, again, the stuff that we don't like to think about, the human resources, the tacit knowledge, the lived experience that leads to good operations?
Yeah, I mean, it's hard to say. It's a tough question. I mean, absolutely, there have been well-run sodium reactors. Another example is FFTF, which is right here in Washington State. I've talked to people who operated that reactor, and they said it was the most boring reactor you could imagine operating. It just responded quickly to any changes. It was single-phase flow instead of boiling water or anything steam and so on. And it was just super easy to operate and worked great. And they really did operate that thing well. It was not a commercial reactor. So yeah, we certainly know that it is possible to run a sodium cooled fast reactor in a way that works well. What we don't know is what the fleet performance is. Like, if you build 100 of them, what's the average capacity factor? That just can't be known. There's plenty of reason to believe that it can be brought up to be reasonably high. Now, and I also want to mention there's other types of breeder reactors as well. I mean, ones we haven't talked about at all are the slow neutron breeders, which use thorium. If you use thorium, you can breed with slow neutrons. That's the unique thing about thorium. And we've built numerous thorium breeder reactors. Indian Point 1, a PWR, was a breeder reactor using thorium in that initial core. The Germans had that gas-cooled thorium reactor that Noah was talking about. The molten salt breeder reactors are all graphite moderated, intending to use thorium to breed. And in fact, Shippingport, Rickover did a huge project called the Light Water Breeder Reactor Project, using Shippingport as the fourth core, where they demonstrated that you can actually breed in a PWR if you put thorium in it. And so there are a bunch of other approaches to get this capability of breeding, where you extend the natural resources out by a factor of 100 or so, using other types of reactors. And so those are all still kind of like in the mix. Like, certainly we know we can operate PWRs well. And that was sort of Rickover's argument, was like, well, sodium might work, but it also might not. And wouldn't it be nice to have a backup plan with a reactor that we all know and love, the PWR, which he obviously, is a big part of. So it's a fair point, and having that as like an option is certainly useful. So there are ways to operate other types of reactors in a breeder mode that aren't necessarily sodium cooled fast. So it's kind of like, yeah, we know we can build sodium fast reactors that operate reasonably well. We think it's reasonable to think that they can compete with like an LWR, but it hasn't really been proven beyond any reasonable doubt. It's certainly proven a lot more than reactors that haven't been built or operated, but and there are reasons to think that, like, well, it is challenging. There have been lots of problems. It's not a slam dunk. Like, if you start up a new sodium cooled reactor, you don't know if it's going to be having all sorts of operational boondoggles or if it's going to be running smooth. Like, it's kind of a crapshoot at this point. Like, I'm sure there's ways to do it well and to do it poorly, but knowing that in advance is very challenging. So anyway, that's sort of my. I just had to mention other types of breeders before we got to the end.
For sure. No, and I agree. That sounds like it might be simpler to leverage the existing, proven technology. But I guess the rationale is just not there because there's not the constraint on fuel. The fuel costs aren't high enough.
Yeah, and also, the thorium breeders breed less quickly, so the breeding ratio is lower. Fast neutrons can breed more atoms per reaction, so that's kind of what held them back. It was like, well, if we're going to do breeders, let's do the ones that can ramp up really quickly. But if you want to ramp up a little bit slower, then those slow neutron breeders are perfectly sufficient. But yeah, I mean, again, the major constraint has always been it's just cheaper to mine enrich uranium or not. Just mine uranium, put in the reactor, and get rid of it. Like, the once through cycle is simpler and cheaper than breeding. And until uranium gets more expensive, that's probably how it's going to be. That's like the real major conclusion. And there have been studies that say, like, well, how expensive does uranium have to get before recycling and breeding makes sense? And so people have come up with estimates like 3 times or 6 times whatever the current price is, and that would be the break-even point. So as that happens, we'll see more and more people get interested in breeders. We also have, France was interested, as you mentioned. They just don't have a lot of natural resources of uranium at all. India has basically no uranium, but they have tons of thorium. And the only way to utilize thorium appropriately is with a breeder reactor. And so they want to get into breeding for that reason.
All of this, though, unfortunately, does seem like nuclear already does suffer from, and in terms of the operational economics, it suffers particularly when there's a glut of natural gas and distorted energy only markets with zero marginal cost renewables jumping on and whatnot. But it does seem like this will ultimately drive up price. Like, there's still, I think it was Levi Strauss who said it, the too cheap to meter thing, and it's been sort of used to tar nuclear by holding it up to these impossible standards. Like, it was one guy that said that, as far as I know. But we all dream about a cheap, abundant, affordable. I think limitless is a bit silly, but nuclear energy in order to sustainably power a high living standard for all of humanity. But it just doesn't seem like there's necessarily a cheat code there, despite how much we kind of desire it. If we do end up breeding and reusing fuel and using tailings, likely it's going to add to the cost, not lower it.
Yeah, and again, it's like, oh, if fuel were cheap or free, that would reduce cost by 5%. Is the reality? The operating the machines is the hard part in nuclear. So yeah, it's not like breeding is just going to bring in the too cheap to meter thing that old Lewis Strauss, he said that to us, to the science writers dinner. And he was like, we'll do supersonic underwater travel and we'll cure all diseases and electricity will be too cheap to meter. And like, no journalist ever says, oh, nuclear, too cheap to meter. They never say like, oh, diseases once touted as, diminishing forever. Like, that always annoys me. But anyway, no, you're right. Breeders are not like a free pass to economical nuclear. They allow a large expansion of nuclear without depleting the resources. They make nuclear effectively renewable. You can use super low grade fuels like seawater uranium or the uranium in granite. There's 20 times more energy per kilogram in granite than in pure coal if you use breeder reactors. So you can literally, so Weinberg famously said, well, burn the rocks. And he meant, we'll just take the trace uranium and thorium out of the rocks and burn it in breeders. It'll last forever. And if you just mined granite, you could power the whole world moving less rock than we currently move for fossil fuel. So it's like, it's really an incredible resource. It gives us an end state. It allows us to grow and say that nuclear is completely sustainable and will be forever. But it is not. It doesn't bring you cheap operation. And right now our big problems are construction and operation costs. And so those really have to be the focus. And if we do get like this 5 or 10x expansion or even a 2x expansion of nuclear worldwide, then I mean, then we're going to really have to start considering breeding. And so it's appropriate and right for people to be thinking and working on breeders now. It probably shouldn't be the major focus of the overall industry. Like, someone should be working on breeders, but it shouldn't be everybody working on breeders, which I think is roughly how it is. So
No, so this was interesting because this did come up at the Net Zero Nuclear Summit on the sidelines of COP28. I was given the opportunity to moderate moderate the panel with Tim Gitzel of Cameco and Clay Sell of X Energy and Poneman. This is going to test my memory. Dan Poneman of Centrus and Boris. Oh God, Boris. Sorry, I'm forgetting your name. Of Urano or Urano. No, okay. I've reached my limit. But that was the question being posed. Like, if we are going to, meet this pledge of 3xing nuclear energy, like, how's that going to look on the fuel side? So you were saying if we double or triple, before long, we would have to start thinking about breeding. Is that accurate in terms of?
Well, yeah,
I know there's a lot of variables here.
With mined resources, like, when the price goes up, people go looking for it, and inevitably they find more. So there's estimates right now. They're in this thing called the Red Book that say how much uranium reserves every country has, and it has been famously wrong. Like, every single time someone goes out looking for more uranium because the price goes up, they find a bunch more. So there's very likely a lot more uranium than we even know about today. It's kind of how things tend to happen, and that's the history of what happens. Whenever we go looking, we find more. That obviously won't happen forever. So is it 2-3x? 2-3x we can handle without transitioning over to breeders, I'm guessing. But if you're talking 5, 10, going up to half the world's energy, then you absolutely are going to need to do something with breeders. So, I mean, I don't know exactly where the cutoff point is in terms of like what level it does make sense, but it's going to be coming along, and it'll take time to develop those breeders and get the fleet experience. So, like, we should be, building and operating, again, handfuls of them, so that we can make sure we can get them up to that economic, so we can operate them well when they're needed. And if it turns out that they operate better than light water reactors, great, we'll just build more of those. So, like, it's important for people to be working on them now. But again, it just shouldn't. It doesn't really matter until we're at least 3x, probably more like 5 or 10x is when it's really going to be needed.
That's yeah. I think that despite it's hazy and it's, as you're saying, it's very hard to predict. Given the more we look, the more we find. But I think that's important for the listenership to hear the kind of time horizons for the necessary development of this technology. Nick, that was fascinating. I learned a ton. I've been engaging more with sort of Gen 4 stuff recently, and it's been useful. It's an important context. It certainly consumes a lot of hot air in terms of what we end up discussing, and maybe for that reason I've been prioritizing other things. But very grateful to have your encyclopedic knowledge there to get a deeper understanding. I'm sure my listenership is grateful too. So thank you once again, my friend, for making the time.
Absolutely. Thanks for having me on.
Anytime.